Okay, for this next question, the second question one, we have another spaceship, this time going in orbit around a different planet. We've got the period. Remember, period is capital T, which I've got written down here. It's a certain height above the surface, and the planet has a radius. So again, just like in the previous question, we need to, when we are considering the equations, take the total radius from the center of mass of the planet, which is the radius of the planet plus the height of the orbit added together. Cool, so let's have a go at doing this question. It picks up from the same spot as last time, so we need to be able to, what is the question? Calculate the mass of the planet. So to do this, we need to again equate these two things together. That this object is in circular motion, there is a force on that object towards the center, and that force is provided by the force of gravity. So call this mass the satellite, mv squared over r, and remember that's the total radius, is equal to g mp for planet times the mass of the satellite over r squared, again total radius. Let's do those same cancellations. As you can see, this is the same working as we did for the last question, so it's good if you become familiar with what we're doing here. Okay, now there's this whole velocity thing over here. We need to get rid of that because this is where the time period comes in. So the time period is the time it takes to do a full orbit. So one full orbit takes this much time, and that orbit, that there is the circumference of the circle. So what we need to do is replace this velocity and get time period in there. So the way we do that is with the velocity equation. Velocity is distance divided by time. We can replace distance with the equation for the circumference of a circle, 2 pi r, and again it's the total radius, divided by, now because it's one orbit, we can replace little t with big T for time period, and we can sub all of this here in place of v up here. So this becomes 2 pi r over t squared equals g mass of the planet over r, and I'll do all this stuff. Don't forget to square the t at the bottom as well. Equals g in mass of the planet over r. So we can now rearrange this and make mass of the planet the subject. P. So I'm going to do two things. The r's on the bottom, so I'm going to bring that up to the top. So it's squared, we're going to multiply it by another r, so we get r cubed. And then here I'm going to take the g from the top and put it down the bottom, so we get gt squared. You can do substitutions up here earlier if you aren't so happy with the rearranging equations. I love rearranging equations, so I like to do the substitutions right at the end, which is where I've got to, well, with one more exception. So remember that the mass of the planet is 4 pi squared, and little r is a combination of the radius of the planet plus the height of the orbit, and all of that needs to be cubed. Gt squared, and then now we can do the substituting, and there's a whole lot of substituting to do. 2 times 10 to the 3 times 10 to the 3, don't forget to cube all of that. Cool. And then 6.67 times 10 to the negative 11, and here is our time period. Now I'm going to put all this in extra brackets so that I can just enter it into my calculator like this with all the brackets. And remember to use the EXP button if you've got it to do these exponents. Cool, and if we bung all these numbers into your calculator, you get a mass for the planet of 3.4 times 10 to the 24 kgs. Then there's a second part to this question, which I'll just explain. So on the return journey to Earth, the spaceship goes past a different planet. The spaceship's path is shown in the diagram. Explain how the spaceship's speed changes as it gets closer to the planet. Well, if you think about it, when the satellite is out here, it's much higher, much further away from the planet. So as it comes closer to the planet, it loses gravitational potential energy. And that gravitational potential energy must go somewhere, and where it goes is into kinetic energy. So as the spaceship gets closer to the Earth, the gravitational potential energy gets turned into kinetic energy. So since the kinetic energy goes up, that means the velocity of the spaceship must also go up. And that's it for this one. On to the next question.